Okay, so our first round of examples, we're going to look at examples for biasing. So the first structure we're going to look at is a stacked transistor configuration. We've got two transistors here, VDD of 5 volts here, going onto a minus VSS of minus 2.5 volts. We've got the transistor at the top biased with a gate of 2.5 volts, the transistor at the bottom biased with a gate of 0 volts. So for this case, 0 volts can go on the second transistor because we have a minus 2.5 volts here, right, for VSS. So these are NMOS devices, so typically we'll start from the most negative supply and work up. So looking at this structure, we actually can make an equation for V2 in terms of the current, this resistance, and this voltage. So we don't know ID for this circuit. We do know the device's parameters, Kn prime W over L, 1.5 milliamps per volt squared, and VTN of 0.9 volts. This transistor here, we'll call this one Q1, is the same as Q2. Those two transistors are equal. So for this problem, we're asked to find the voltages V2 and V1 for this bias setup. Okay, so writing the first equation, V2, we have V2, minus 2.5 volts, so plus 2.5 volts, is equal to the current ID times 1 kilo ohm, the 1 kilo ohm resistor. So that's the first equation. So we can express ID, we can re-express ID in terms of V2. The second equation, we can assume saturation for these devices. We can go back later and check saturation, but we can assume saturation and use the saturation current equation. ID 1/2 Kn prime W over L VGS, and we'll do VGS2 here because we're trying to solve for V2 first, minus VT, which was 0.9 volts, squared. So this current right here is actually equal to this current here when we rearrange this equation. So setting the two equations equal to each other, we're going to have ID here is going to be V2 plus 2.5 volts over 1 kilo ohm. So V2 plus 2.5 volts over 1 kilo ohm. And that is equal to this right here, 1/2 Kn prime W over L, where Kn prime W over L is 1.5 milliamps per volt squared. VGS2, which is what we're solving for, minus 0.9 volts squared. So VGS2 in this equation is VG minus VS of transistor 2. VG of transistor 2 over here is 0 volts. So this actually goes to 0 volts minus VS of transistor 2 is V2. That's what we're trying to solve for, V2. So we can actually replace VGS2 here with 0 volts minus V2. So now, looking at both sides of these and trying to solve for V2 here, we'll come up with a squared term. So we're going to have 0.75 times 0 minus V2 minus 0.9 squared. That's this side of the equation. And that's equal to V2 plus 2.5. Note the 1 kilo ohm comes over to this side, and the kilo ohm and milliamp units will cancel. So 1,000 times 10 to the minus 3, and that'll go away and become an absolute 0.75. Okay, so now solving this here, we'll have V2 squared plus 0.467 V2 minus 2.523 equals 0. And from that, you should get V2 equals 1.84, minus 1.84, volts. Okay, so that's the first one. Now, the second part is to find V1. So you can observe this V2 is minus 1.84 volts, which means VGS2 is actually plus 1.84 volts, right? So VGS2 is equal to 0 volts minus 1.84 volts, which is equal to 1.84 volts. Now, all we have to know is that the same current is going from Q1 through to Q2, and they have the same transistor size, Q1 and Q2, same Kn prime W over L, same threshold, so VGS1 should equal VGS2. So 1.84 volts, VGS1 actually equals 1.84 volts. And since we know it's 1.84 volts, since we know VG of 2.5 we can solve for V1. So VG is 2.5 volts minus V1 equals 1.84 volts. So V1 equals 0.66 volts. All right. So there you go. We always calculate based on VGS's. Note that we never made V1 and V2 in the same equation, and we never made a dependency for the current on VDS, right? Because that would be a weak dependency on drain to source voltage. So we were using VGS's to solve this. We were using the VGS of Q1 and the VGS of Q2, never a VDS to solve this. We were assuming saturation current here to get this equation, and we were actually working from the bottom up because they were NMOS devices. All right, you can go back, I'll leave that to you, and check that with this V2 and V1, these devices are actually in saturation. So go back and check that, of course, VGS is greater than V threshold, and that VDS is greater than VGS minus VT. That should be the case to hold true to be able to use this saturation current equation.